So another example here, right? This time we're going to end up using a lot of our skills dealing with complex numbers, addition, subtraction, multiplication, division, all in the exact same problem. So it says perform the operation and write the result in standard form. We have 2i divided by 2 plus I plus 5 over 2 minus I. Well, one thing to keep in mind, again, guys, don't forget your rules of algebra that you have been using for years now still apply. If we want to add two fractions, we must get a common denominator. All right, to add fractions, you must have a common denominator. So, what's the easiest way to get a common denominator? Well, we would take our first fraction and multiply the top and bottom by the denominator of our second fraction. And we would take our second fraction and multiply the top and bottom by the denominator of our first fraction. Okay, so I'm taking the first fraction, I'm going to multiply it by 2 minus I over 2 minus I, and take my second fraction, 5 over 2 minus I, and multiply by 2 plus I over 2 plus I. All right, so we know how to multiply fractions. Multiply numerators times numerators, denominators times denominators. In my numerator of my first grouping, I have 2i times 2 would be 4i minus 2i squared. My denominator, 2 times 2 is 4 minus 2i plus 2i. Notice that when we FOIL, the products of our outer and inner terms add to 0 because they are complex conjugates of each other, minus an I squared. And in my second fraction, my numerator is going to be a 10 plus 5i. So I have 4i minus 2i squared over 4 minus I squared plus 10 plus 5i divided by 4 minus I squared. So the good news is that we have a common denominator now, which means we can combine these fractions. What's even better, however, is that we can continue to simplify these. Subtracting I squared is the same thing as subtracting negative 1, and our denominator, common denominator, is actually going to be positive 5. Also, in my first numerator here, minus 2i squared, I can rewrite that as plus 2. 2 plus 4i over 5 plus 10 plus 5i divided by 5. And because we have a common denominator, we can now add our two fractions by adding the numerators and keeping our denominators the same. To add the numerators, all we have to do is combine our like terms. 2 plus 10 gives me 12. 4i plus 5i gives me 9, leaving me with 12 plus 9i divided by 5. Now, this would be a completely acceptable final answer. All right, none of the fractions would simplify. However, if you would like, you certainly could split up your real parts and imaginary parts using the distributive property of division. 12 fifths plus 9 over 5 times I. All right, lots of good operations with complex numbers in that problem. Let's see another application of complex numbers. So this says use the quadratic formula to solve the quadratic equation, right? Here we are trying to find the zeros of a quadratic. And whenever you go to find the zeros of a quadratic, the very first thing you should look to do is to factor. However, in this case, notice that there aren't any factors of 10 that add to give us negative 6, all right? No combinations of factors of 10 that add to give us 6. So this is actually not factorable. And if we come across a quadratic that is not factorable and we are still trying to find the zeros, we can do so by using the quadratic formula. All right, use the quadratic formula to solve the quadratic equation. And as you guys know, the quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So this gives us the roots or the zeros of our quadratic. Plugging in, we get negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 10, all divided by 2 times 1. We can continue to simplify. Notice 6 squared is 36 minus 40. 36 minus 40 gives us a negative 4 inside of our radical. We have negative 6 plus or minus the square root of negative 4 all divided by 2. Well, we see a negative inside of a square root. And as we know, negatives inside of square roots mean imaginary solutions. Yes, we're going to have imaginary zeros in this case. So we can simplify that. The square root of negative 4 is root 4i, which becomes 2i. We have negative 6 plus or minus 2i divided by 2. And using our distributive property of division, we can divide each term in the numerator by 2, leaving us with a final answer of negative 3 plus or minus I. So this quadratic, while it does not have any real zeros, okay, it does not have any real solutions, it has two imaginary solutions. One is negative 3 plus I, the other is negative 3 minus I. And if you were to plug those in for x, you would indeed get out 0 for your answer. All right, so we can use the quadratic equation. Now we can find not only the real zeros, the real roots, but we can also find the imaginary roots as well.